classifying elements on the periodic table is by blocks. So blocks are actually designated based on quantum electron configuration. This is extremely helpful because these blocks actually determine a lot about properties and elemental behavior and relate to real quantum configurations, which relate really well to real chemistry and our modern view of the atom. So we are doing an activity in class where you're looking at filling quantum diagrams for each element. You're then going to lay the elements down and arrange them according to their arrangement in the periodic table and kind of look to answer some questions below. So what you should generally notice is if you compare some configurations of group 1 and 2 elements, the letter or the sublevel that you added your last electron to is always S. If you look at groups 3 through 12, you're always putting an electron in the D last. And if you look at groups 3 through 18, you're actually putting your last electron into a P sublevel. Sorry. So you can actually make some predictions about electron configurations based on knowing the row in the periodic table that an element is in, and also knowing the sublevel that the last electron goes into. So if you actually look at your period number, any element in group 3, in period 3, for example, will always have its last electron being put into the 3 something orbital. So if you look at some other elements on here, look at a large element like number 76, if you actually just put your finger on element number 76, without even doing its quantum configuration, you can tell me where its last electron is going to go. It's in period 6, so that means it's going to go in the 6th PEL. And because of where it is on the table, everybody in group 3 through 12 gets their last electron put into a D orbital. So that's going to be the 6th D where that last electron goes. We kind of talked before about how some elements such as iron have really weird really weird Bohr configurations if you don't understand the quantum stuff behind it. If you just, took 26 electrons and laid them out like you might expect, you might think that iron would actually be 2, 8, 16. It's 26 electrons kind of plopped in there. But it's not. It's 2, 8, 14, 2. And that last electron, we can make a prediction, is going to go into the 4D. Just to kind of review this with you, why the heck does that happen? So if we have 26 electrons, and I'm going to fill them according to my diagram. I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. At 18, I'm at the 3P. I'm going to go to 4S. 19, 20, 21, 22, 23, 24, 25, 26. So what we see here is we have 1s2, 2s2, 2p6, 3s2, 3p6, 3d, 1, 2, 3, 4, 5, 6. Oh, and 4s2. This is what gives us that Bohr configuration of 2, 8, 14, 2 by adding those numbers together, looking who's in the same principal energy level. So this can kind of be a helpful way of looking at what electron configuration should actually look like, since the Bohr configuration kind of breezes over that a little bit. So this gives us something we call in the periodic table the blocks. And our blocks are as follows. You should know that everything in groups 1 and 2 are considered the S block, meaning their last electron goes into block, in this case, S. Okay? So whatever letter you're talking about here goes in that blank. Anybody who falls in this middle group here, their last electron goes into block D. Anybody in this P block over here, the last electron goes into block P. So we also have down here what's called the F block. We don't deal with those a ton, but those are just really big atoms who actually do have their last electron put into an F sublevel. So we can make a nice prediction just by looking at iron or iodine, for example. Iodine, for example, is in the 5th period, and it is in the p block. So iodine's last electron will be in the 5p orbital. So a nice prediction that we can make simply by looking at location on the periodic table.